I did. I was working on that, but then the other things you
Okay. Where is half the class? What's happening? Fermentation?
Yeah.
Okay, we're suing Dan O'Sullivan. Is that what we're doing? Okay. All right, let's get started. We're back to spectroscopy. So you had a little bit of a change in subject. You had moisture with Gary, but let's finish spectroscopy. I'm gonna spend today and 2 lectures next week and finish up spectroscopy. When is your midterm? Friday, not Monday. Monday or Friday?
So next Friday.
I'm so excited.
Okay, so we'll finish up spectroscopy and everything from the beginning of the semester through spectroscopy will be covered with the exception of moisture. So the lectures that Gary covered on proximate analysis and moisture will not be on the midterm. I will reiterate that next week, just that you remember. But all of the introductory chapters, all of chromatography, mass spectrometry, and spectroscopy will be on the midterm. I know I heard that the quiz 1 was brutal for most of you. That's okay. Like I said, it's equivalent to a lab report. Don't worry, you have a lot of opportunities for grades, but please do study for the midterm. It's 100 points. If you have questions, let me know. I'm happy to answer questions via email or even have a Zoom call with me to answer questions. But please be prepared to the midterm. You have a week from today to study. I encourage you to start studying and start looking at last year's midterm. It's not going to be the same. It's going to be very similar in terms of, context and how the questions are formatted. So after you study, try to solve that midterm. All right. And if you have questions, don't hesitate to ask. Okay. So let's go back.
Did someone put a question in the chat for you, or is that something?
Was there a chat question? Is the midterm in class? Yes, it is in class. You come here. I will be also here and a couple of TAs helping proctoring. So yes, it will be in person in class. And if you come 10 minutes early, we can start if you need the extra time. It should be done in 50 minutes, but so that you don't have to rush. If you come 10 minutes early, we get started with the midterm. Okay, so bringing you back to spectroscopy, I introduced it briefly, and then you had Christine covering IR. I'm going to step back and talk about spectroscopy as a whole, and then next week we'll do UV visible absorption, and then we'll do the atomic absorption as well, the theory behind it. You already did the lab, so it will be kind of a revision for you. All right, so under spectroscopy, we consider species. So either atoms or molecules can absorb or fluoresce. They interact with the light. So they will have the radiation interaction with the matter. Matter would be molecules or atoms. The interaction can be absorption, can be emission, can be light scattering, can be diffraction, can be refraction as well. And the region of the electromagnetic spectra is what dictates if we're looking at absorption of visible light, UV light, IR. We mostly care about UV, visible, and IR spectroscopy in food analysis. So we're not going to look at other regions in the electromagnetic region. So one thing I want you to remember, the shorter the wavelength, the higher is the frequency or the energy. So keep that in mind. That's a very important thing to remember. Shorter wavelength, higher energy. Okay, and we're going to talk about that in more detail. All right. So, okay, let's see here. All right. So in spectroscopy, we're going to learn about UV vis absorption. You already learned about infrared. You had the lab on atomic absorption. We're going to talk about that. We will talk about the theory of inductively coupled plasma emission, ICP. That's emission spectroscopy. We're going to talk about fluorescence. We are not going to cover NMR in this, but it's part of spectroscopy. It requires probably a whole semester to understand NMR. It's not going to be part of this class. And mass spectrometry is bulked in your textbook as mass spectroscopy / spectrometry. There is no light interaction as you have learned in mass spec. So, but you get spectra, but it's different kind of spectra. It's ion spectra rather than light-related spectra. So you already covered that in with Gary with the mass spec, and we did the mass spec lab. Okay, so there are different applications for spectroscopy. Let's think of a few. Hallie. Qualitative, very good. With qualitative spectroscopy, what do we normally look for qualitatively? What will be like the purpose of the experiment with qualitative spectroscopy? What are we after? Ian? Identification. So oftentimes we're trying to identify based on the spectra, whether it is a UV spectra or a visible light spectra or a fluorescence spectra or even an MS spectra. So identification. What else with qualitative? Medora? So we have quantitative. We do a lot of that. So we did the caffeine, we used UV absorption to determine caffeine concentration. With IR, we also use quantitation of composition. Once the IR instrument is calibrated, it can give you quantitative data. So definitely getting the emission and the absorption and looking whether in the UV range or the visible range or the IR range, we can calibrate and we can quantitate. In qualitative, we set the identification. Another thing than identification, you are also doing structural elucidation sometimes. You determine, okay, I have a ring, a phenol that absorbs light. I have a carbonyl group. I do have a amine group, a carboxyl group. You can do structural elucidation with spectroscopy. Let's see what else we have. So qualitative and quantitative. Under qualitative, we have the identification and structural elucidation. Under quantitation, we have compositional analyses. And also we have quality assurance and forensics. So sometimes you want to know if you remember the outbreak of melamine, for example, a few years back when melamine was used in pet food and infant formula. It went undetected because the method for determining protein was based on nitrogen. And melamine has nitrogen in it. So it went undetected and it was considered as protein. But then if you do IR of an infant formula versus an infant formula that is adulterated with melamine, you see a unique spectra for melamine adulteration. So a lot of uses for spectroscopy. It's key in food analysis. That's why we're learning about it. So to learn spectroscopy, we have to remember a little bit about physics of light. I don't know, not many of us have a love for physics, but here we are. We're going to go a little bit about basics of light. because it's important to understand that, because all spectroscopy is light matter interactions. So we need to understand characteristics of light, and light has a wave characteristic and a photon characteristic. So the wave of light has an electric field and a magnetic field. So that's the basics of that. We care much about the electric field as we utilize it to define lambda, which is wavelength. So wavelength is between two maxima. This we call an oscillation, going from maxima to minima. That's one oscillation, then another oscillation, then another, then another. That's how the wave moves. And the distance between this maxima and this maxima is called the wavelength. The shorter the distance, the more oscillations you have in a given time. So basically, shorter wavelength, you have more oscillations. That's why you have higher frequency. Okay, so shorter wavelength, higher frequency. So these things are very important for you to remember. So wavelength, oscillation, and the more oscillation within a unit time and a unit distance, that indicates frequency. Okay, so these are the things you want to remember here. Another thing is the amplitude. So the amplitude is the magnitude from the base to the maximum. So that is called amplitude. So here in this figure, you want to remember a few things. Lambda, which is the wavelength. Frequency, how many oscillations you have per unit time and unit distance. And then the amplitude, which is the distance, the magnitude of the electric vector, basically. Okay, so these things you want to remember. So when we're looking at wave-like properties, there are a few things that happens: interference, diffraction, and refraction. So let's look at interference. This is important in IR spectroscopy. I hope Christine talked about this a little bit. But in an instrument, you can amplify the signal. The way you amplify the signal is you put mirrors within the instrument, and then you have several wavelengths combining with each other, having the maxima meet at the same time and the minimum of the oscillation meet at the same time. Then you have amplification of the signal, you enhance sensitivity. So in spectroscopy or spectroscopic instrument, you can get this amplification by using mirrors. You can also get cancellation to avoid interference from other wavelengths that you don't want them to be recognized, so that you can avoid like noise, we call it, so that you only focus on the compounds of interest. So in cancellation, you have mirrors in such a way that the maxima meets with the minima, and then they cancel each other. The amplitude cancel each other, and then you don't have any signal that goes into your sample at a particular wavelength. Okay, so that is one type of property, which we call it interference. Diffraction, I talked about it briefly last time. It's when you have an incident beam hitting a diffractive grating system. So the beam diffracts into multiple wavelengths, individual wavelengths. So therefore you can measure absorption at different lambdas, rather than just having a beam that has multiple wavelengths together. In quantification, we really have to have a monochromatic light. When you're doing quantification, you really want to measure at a specific lambda. That is part of Beer's law that we will talk about next week. Beer's law dictates that for quantification, we have to measure at a singular lambda. So diffraction is very important in quantification, that the beam of light will be broken down into multiple waves with unique wavelength. So that's diffraction. It's very important spectroscopy, very important in quantification. The refraction of light, we use it a lot in refractive index, and we relate that to total solids content or total soluble solids. So it's very strong tool, and the refraction is when the beam of light hits a different media, it refracts, changes direction, changes the angle at which it is traveling. That change in angle can be correlated to concentration of solids, for example, in the medium. So it's used very commonly for total solids, your refractive index, and also it's coupled with a liquid chromatography, especially when doing carbohydrate analysis. You have a refractometer as your detector. Okay. Light can also be described in photons of light, particulate properties. So basically, the wave consists of pockets of energy. So photons are pockets of energy, basically. And the energy of the photon is defined as E for energy equals H, it's Planck's constant, it's a constant, and then the frequency. So the higher the frequency, the higher is the energy. Again, the frequency is the number of oscillation that happens within a unit distance and unit time. Okay. From what I talked so far, can you tell me what is a monochromatic light? Mono. Yes, Kevin.
One wavelength.
Yes. One wavelength. A monochromatic light is one wavelength, one lambda, or light that has lambdas that are very, very close to each other in length. Okay. What is a mono? Okay, here's the definition if you want to write it down. Electromagnetic radiation composed of waves having a single frequency and wavelength. Okay, so having equivalent energy, basically, traveling together at the same frequency, same oscillation. Okay, so that is monochromatic light. What is a monochromator? I don't know if Kat talked about this in atomic absorption when she covered the atomic absorption unit. You have the spectrometer in the atomic absorption unit, and in there is a monochromator. What does the monochromator do? Yeah.
It filters out all other lights except for one type.
Absolutely. That's a very, very good way of saying it. So in a monochromator, what happens, you need to have a grating system or a prism or both sometimes. So you need to have the diffraction of light happening. Okay, so your beam of light, usually we use mirrors because we need everything to be inside of a small box. So we utilize mirrors to make the space smaller. So you have the source of light, your lamp. It's giving, we call it the incident beam. This is a mirror. It hits the mirror and it gets reflected onto a grating system. Sometimes it's a prism. So the grating system is going to break it down into those different waves of light of different wavelengths. And then you have that filter that you can adjust to allow a particular set of waves to come out with the same wavelength. And then again, it hits a mirror, gets reflected, and monochromatic beam then hits your cuvette, wherever your sample is. What is the cuvette in atomic absorption? Remember what the cuvette was made up of?
Just whatever element you're analyzing for, so like iron.
Okay, let me rephrase my question. I might have confused you with what I'm asking. You know what a cuvette is? Sample folder where you put your sample in. What was the cuvette in atomic absorption? Adora, go for it. This is the area of the flame. This is the flame, is your cuvette. So your sample is actually going into your flame. You don't have a tube, you don't have a cuvette, you don't have a physical entity that the sample is in. Your sample is aspirated into that flame, and then you get atomization happening, and then the light hits the sample in there. Okay, so then your monochromatic light is hitting your sample, and then the sample absorbs, and then the light that is not absorbed reaches the detector and get converted into electrical signal, and calculation of absorption occurs. So again, it has to be monochromatic light for quantification to happen. All right, good. A photon flux. So what is a photon flux? It's basically number of photons that flows across a surface, across a unit area perpendicular to the beam. So how many photons are hitting that unit area per unit time? That's what the flux is. The brightness has to do with the intensity of the light. And the intensity of the light is basically equal to the energy, which is directly related to frequency, directly related to the wavelength, by the area, how much energy is hitting a particular area per unit time. So you can adjust brightness in your spectrophotometer to enhance sensitivity, but there's always a limit. Every spectrophotometer has a limit in threshold. But brightness is something that you can control to enhance sensitivity, power of detection. Okay. This is just to remind you that with shorter wavelength, you have higher energy due to higher frequency. So you can see that you have more oscillations in a shorter distance, then you have shorter wavelength. And as you go down in the spectrum, your wavelength increases and the energy decreases. So it's an opposite relationship. And in food analysis, again, reminder, we work with ultraviolet, visible light, infrared. That's where we work. There's the near infrared, and there's the mid-infrared that you covered with Kristen. So if we want to talk about absorption and emission, we always think of light as particulate properties. So absorption of photons, emissions of photons of light, rather than thinking of it as electric or magnetic field. We just think of it as pockets of energy that are absorbed by a compound and sometimes emitted by a compound. So we always measuring this absorption of energy and the emission of energy. That's what we measure in spectroscopy. So absorption is when a photon of light hit an electron in the outer shield, in the outer shell, basically. So when an energy or a photon of light hit an electron in the outer shell, the electron gets higher energy, so it gets excited, and then it moves to a higher shell. So that's called the excited state. But it doesn't stay there long. It goes down to ground state. Sometimes when it goes down to ground state, it just emits heat, energy in the form of heat, which is very, very small amount of heat you cannot measure. So in this case, we just measure absorption of light. Sometimes the compound, a molecule, or an atom can fluoresce, meaning when it's going down from excited state to ground state, it emits a photon of energy. It emits light, but there's also dissipation of heat. So the energy that it emits as light is lower energy than the energy absorbed. So one thing you need to remember, underline, score, whatever you want, bold, is the emitted energy has a larger or longer wavelength than the absorbed light. So when we're measuring fluorescence, there's always in the procedure, when you go read an article and they're measuring fluorescence, they give you two things. They give you the absorption wavelength and they give you the emission wavelength to set up your instrument. So you will be setting it up so that the compound or molecule absorb at a particular wavelength, and then setting it up to measure emission at a particular wavelength. And always emission has higher wavelength. Okay, let's see if you're paying attention. Why does it have higher wavelength, the emitted energy? I need that to be ingrained in your brain. Okay, Medora. Why does it have less energy? Kevin?
The heat.
We are going from excited state to ground state by emitting some heat as well. It's always, the molecule is emitting some heat. Part of the energy for that particular molecule is in the form of light. So not everything can fluoresce. Compounds that can fluoresce go down to ground state by emitting a little bit of energy in heat and a little bit of energy in light. Because it's less than the light absorbed, your wavelength will be longer. So when we're measuring fluorescence, we set, let's say, our absorption at 280, and then our emission, let's say, will be set at 320 or whatever. So longer wavelength when we're measuring emission. Questions? Okay. So a molecule is struck by a photon, may absorb the photon energy, but not every molecule absorbs light, right? Some molecules absorb light. Some molecules absorb light at different wavelengths. But the light absorbed, the energy absorbed is equivalent to the energy gained by that atom or molecule. So the same amount of energy that the molecule got hit by, it absorbs. And it goes from ground state to excited state. So basically the same amount of energy that hit it will be absorbed. Either it absorbs that energy or it doesn't, depending on the absorption spectrum of that molecule. Sometimes it has to be at 280, sometimes it has to be at 254, sometimes it has to be at 300 nanometer for the energy to be absorbed. So that's what the last point here means. The internal energy content of the molecule does vary in a series of discrete steps and not in a continuous manner. So a compound might absorb at 280 and does not absorb at 300, but then absorbs at 340 again. You might have a spectra that look like this. So here is absorbing at 280, here is absorption at 300, and here's absorption at, this is 0, so no absorption here. And this is, let's say, 340 nanometer. So it's not continuous. It doesn't mean that with higher energy, you get higher absorption. No, it doesn't mean that way. So there are discrete steps, allowable energy levels each atom and compound or molecule has. If you hit it with the right energy, it will absorb. If you hit it with the wrong energy, it does not absorb. That's what it means. It's not continuous. And this is a demonstration of these discrete steps. So we have electronic energy, we have vibrational energy, and we have rotational energy. The electronic energy has to do with the energy absorbed by the electron, from the name of it. Electron in a singular atom, or electron in a molecule, the valence electron, the electrons on the outer shell, or the electrons that are in the bond between two atoms. So that is electronic energy. Vibrational energy, is you learned about it already with Christine, it has to do with the vibration of the bonds, stretching, bending of the bonds. So you would have two atoms, at least two atoms, and you have a bond between them, and that vibration, the bonds are always in motion. And if they are hit with energy, the motion increases and there would be an excited state. So that vibration is for molecules in bonds, where you have atoms in bonds. Rotational energy is the energy of the molecule. So all of the atoms and all of the components of the molecule are rotating around the center of that molecule. So that's rotational energy. Okay, so that every molecule, every atom, every molecule, every atom has these discrete steps. The ground state, the first excited state, the second excited state, depending on the energy intensity that they get, but it has to be allowable energy. In atomic absorption, you don't have vibrational or rotational energy. You don't see these sublevels. Okay, this is atom, only electronic energy. In a molecule, you have vibration, you have rotation. So you have the vibration is of a lower energy because this is in IR. IR spectroscopy, you have lower energy because you have longer wavelength than UV and visible. Okay, so it has less energy than UV light or visible light. So you see that those discrete segments are lower energy than the electronic energy. And the rotational energy is microwave radiation. So they're also longer than IR and of course than UV and then visible light. So they are very small pockets of energy. Okay, so that's basically a summary of what I'll be talking about in the next slides, is the differentiation between electronic, vibrational, and rotational energy. I don't see any excitement in the room. You look bored as heck. Well, you know, you get to be a little bit excited, talk about energy. Anyway, so sad for me. Okay, so electronic. So now I'm going to talk about them again to kind of make sure that the concept is fixed for you. So electronic energy, because of its name, it's the electrons that absorb energy and the electrons that are on the outer shells or the electrons that are involved in bonding within a molecule. So these electrons absorb the energy and go to a higher level or a higher shell, energy shell. So, and then there are different levels they can go to depending on the light that hits and the characteristics of the wavelength that hits that atom. So once the energy is absorbed, the whole atom or the whole molecule's energy is increased by the same amount of energy that got hit. They absorb the same amount of energy. All right, and then the other thing I talked about is the energy levels that are electronic energy are within the range of UV visible radiation. So when we study UV visible spectroscopy, we are talking about electronic energy, not rotation, not vibration. So the UV vis is always about the electron jumping to higher electron energy state level, based on the wavelength that hits them and based on their ability to absorb a different wavelength. Okay? No matter what, if the energy does not match the allowable energy, the molecule or atom will not absorb light. It has to be within the allowable energy levels for the molecule to absorb. Hence, we have this kind of spectrum. Okay. The vibration, like I said, it's the molecule, the bonds within a molecule are in constant vibration, stretching, bending. And when they hit with IR radiation, they vibrate more. So they gain this energy. Again, it has to be within allowable steps. Okay, so the first level, vibration 1, vibration 2, 3, 4, 5, etc. Again, in IR, you have to hit the molecule with the allowable energy level in order for it to absorb and have a detection. Okay. And this just simply says that the photons of light that allows vibrational energy are in the spectrum of IR infrared radiation. So that's what here it's telling you. Rotation, like I said, it's the rotation around the center of the molecule, and it is equivalent to microwave radiation. And like I said, microwave spectroscopy is not of interest in food analysis, but you just have to know that rotational energy exists, and microwave radiation is longer than IR, so therefore the energy pockets are also smaller than the vibrational energy levels. Okay, but we don't really care about rotational energy in spectroscopy, in food analysis. All right, so when you have an atom, we only have electronic energy. There is no vibration, there's no rotation. When you have a molecule, the molecule can absorb in the UV light, can UV or visible. It can absorb in infrared region. It can also absorb in the microwave region because it can have electronic, vibration, and rotational energy. But again, it has to be allowable. So this is basically what I drew you here, is it has to be transferred to the molecule, the energy, so that the molecule goes from ground state to excited state, but again, in allowable regions. And this helps in detection of impurities that we talked about when we were covering detectors for LC. So different compounds have different spectra, different allowable energy that allows us to differentiate them from each other. So that's where we do qualitative detection and identification, structural identification. Last bit here is on emission of radiation, which is the fluorescence. Not all compounds or atoms fluoresce. You just have to remember that. You reach excited state, not you. You're obviously not excited today. So the atom or the molecule gets to an excited state, and then it has to go to ground state. It won't stay excited for long. Two ways: either it goes to ground state, dissipation of heat only, or it goes down to ground state with a mixture of dissipation of heat and release of a photon. We call that fluorescence. It fluoresced. So that term, oh, the compound fluoresces. It emits light, basically. So that's what fluorescence spectroscopy is. It's about emission of light, but also always remember that the emission of light is at a longer wavelength than the original absorbed light. So that is the intro to spectroscopy is done. I do have some more minutes. I can start the next lecture. Because you're super excited. Your excitement cannot be withheld. So I'm starting a new lecture. Yes, who did who? You're the least excited in the class. You don't seem excited yet. Huh?
I'm brimming with excitement. I can't wait.
Oh my goodness. You made my day. Okay. It's coming. Let's do UV vis and fluorescence spectroscopy. All right. Aha, some terms from years that you wanted to forget probably. Okay, molar extinction coefficient is constant for all analytes. A highly concentrated sample may result in deviation from Beer's law. Aha, who remembers what Beer's law even is? Incident beam minus exiting beam is equal to the light absorbed by the analyte. Yeah, just give it a go. Come on, Hallie.
I'm just guessing, but all of the above.
All of the above is true. Okay. Anybody? No, I didn't say that. Anybody with an opposing statement? Ash.
None of the above.
A very strong opposing statement that is true. None of the above. Now, do you know why, or you're just opposing Hallie for the sake of opposing her?
Just for the sake of it.
All right, so we're gonna learn about all of this, but molar extinction coefficient is very unique for every analyte. We're gonna learn about that, and it is an important factor in Beer's law. Beer's law is absorption equal A. We call it absorptivity or molar extinction if the concentration is in molarity. And then you have the concentration, and then you have the distance the light travels within your sample. So the distance, for example, of the cuvette, if you have a cuvette, and then your sample is in here, this is B. Absorption equal, it should be A, B, C maybe, like that. But absorptivity, the lengths the beam travel, and the concentration. And that's how we link the concentration to absorption. So absorptivity, A, is very, very unique to different compounds at a particular wavelength. One of the laws of Beer's law is that you have to have monochromatic light. It's very important, otherwise you deviate from Beer's law. Okay. A highly concentrated sample may result in deviation from Beer's law. Oh, that is correct, actually. It's not all incorrect. What was I thinking? So Ash was wrong, Hallie was wrong. Dang. Okay, that's all right. No shaming. We're learning. The only true answer is B, actually. So just to correct your notes there. Yes, that's why we have to work in certain diluted concentrations. That's why we have our standard curve, making sure that it is linear. And then that's why when we're measuring samples, we have to dilute them so that they fit the linear curve. A really high concentration, you would have the molecules interacting with each other. So you would have molecular interactions that will impact their absorptivity. And with that, we have deviation from Beer's law. So B is the correct answer here. Sorry about misleading you for a minute there. Incident beam minus exiting beam is equal to the light absorbed. So what do I mean by that? So I have my light here, whether it is, let's say it's a particular lambda, and then I have a sample, and then I have a light exiting that hits the detector. So that's the incident beam, that's the exiting beam. One would think that this minus this, the incident minus the exit, is the amount absorbed. But it's not. Why not? What happens when light goes in here? Other than absorption, absorption can happen, but what else can happen? Yes, we not necessarily, yeah, I mean, you can have refraction, you can have reflection, you can have scattering of light, you can have so many different things happening when it hits different molecules. So the exit beam has information about the absorbed light, but it's not really this minus this. That would have been really easy. So we have specific equation and log actually to correlate the absorption when the exit beam reaches the detection. There's some calculations that happens here to convert this into absorption value. So it's not simply this minus that. Okay. If in both absorption and fluorescence spectroscopy, UV vis radiation is used, the transmitted beam is the signal measured, a grating monochromator is needed. Go for it, please.
A and C.
A and C, yes. So especially if we're doing quantification, we need this monochromator thing. But if we're not doing quantification, sometimes monochromator is not needed. So the answer here is depending if we're doing qualitative or quantitative measurements. But yes, in fluorescence and an absorption, we're dealing with UV vis radiation. But, okay, there's a caveat. There's a caveat for everything. You can absorb IR radiation too. Okay? So, depending what absorption we are working with, right? So, A might not be correct. And the transmitted beam is not the signal that is measured. Sometimes it's the fluorescence beam. especially the emitted. So in fluorescence, we're measuring the emitted light, not the one that just get transmitted to the detector. And a grading monochromator is sometimes needed when we're doing quantification, but sometimes it's not needed when we are doing qualitative measures, and we'll learn about that. So it depends on the scenario, right? The answer here is not really very clear. It can be none of the above based on what other scenario I give you. I won't confuse you like that in the exam, I promise. All right, so we'll stop here and we'll continue on Monday. Have a great weekend.